Hi everyone, welcome to this M2D2 talk. It's been a while. We were away because we were taking a break to reorganize and working also on a new platform, Balance Portal, um, that I have my colleague Johnny here, who will say a few words about. It be the new platform, the platform where we share the talk and everything else that we are doing. So, Johnny, are you online?
Yes, I'm here. Could you let me share screen?
Sure.
Thank you.
I think you can share your screen.
Yes, perfect. Okay. Um,
Do you want me to stop sharing, Prudential?
no, I
Uh,
should still be able to
I think I
share.
think you should be able to.
Try this. Everyone can see my screen?
Yes.
Perfect. So yeah, I just want to show everyone really quickly. I know lots of folks are on the MTD2 Slack. Um, and we're kind of sending a lot of messages there, but you're also tuning into the videos on YouTube. I know many of you are also reading the blogs. We also have the Learning on Graphs reading group as well, and those recordings. And then we have all of the discussions that are happening on Slack as well. And so over the summer, we decided to kind of aggregate all of the community into a single home, and that's Valence Portal, where you can stay up to date on all of the reading groups. So here you can see all of the upcoming talks. For example, with Amir's talk as well, you would have seen that you can see the talk abstract, you can see the papers that are going to be discussed, but you'll also be able to connect and message with each of the speakers once we've onboarded them to Valence Portal. So in Portal, you can also direct message people. So if I want to reach out to Prudencio, I can send him a message, um, ask him to connect or, discuss research. We also have discussion forums that will hopefully eventually replace the Slack channel that we have, just because we're on the free plan for MTD2, and many folks have been messaging me saying, hey, like our messages are disappearing after 90 days. Unfortunately, that's the restriction that we have on the free plan, but on Portal, everything will always be here. So you can post discussions, ask questions, share your new papers that you're announcing, and you can also search across the entire platform for whatever it is that you're looking for. And you can jump directly into the topic of interest as well. But yeah, just wanted to show really quickly Portal. You'll be able to also add the recurring event to your Google Calendar if you wish. And you can find all of our Zoom links here on the platform. So I'll pause there and I'll hand it back off to Prudencio.
Perfect. Thank you, Jenny. Yeah. So now let's start. Today our speaker is Professor Amir Farimani, joining from the Department of Mechanical Engineering at Carnegie Mellon University. His lab at CME focused on problems at the interface of mechanical engineering, data science, and machine learning. And they use state-of-the-art machine learning and deep learning model to teach AI method how to predict the physical phenomena that happen in material discovery and also in drug discovery. Thank you so much, Prof. Ami, for accepting our invite to speak here today, and looking forward to it.
Okay, great. Thank you so much, Prudential and M2D2 for this invitation. I'm pretty excited to talk about some of our recent advances in AI molecular discovery. And I'll go through a list of the works that we did during the past 2-3 years, and I hope that it could be useful to the community. And please reach out to me if you have any questions or you wanted to collaborate on different topics that we have here. So molecular property prediction is pretty important for many applications. So the most obvious application is drug discovery, which takes a long time, and also it's a multi-million-dollar industry. And one of the biggest challenges in drug discovery is the amount of time that is needed essentially to be able to approve a drug to be in the market. So it has multiple phases: phase 1, phase 2, phase 3, preclinical test, lead optimization, compound screening, and target validation. And to do all of these takes around like 15 years or so in order to do that. So any kind of models or any kind of actually ways to accelerate this pace would be wonderful, and that's a big service to the humanity. And essentially the problem is very difficult. It's equivalent to finding a needle in a haystack, because with only a few elements of the periodic table, you can build millions and billions and trillions of molecules. And then the question is that if you wanted to find a drug that is suitable for clinical trial, I mean, what should we do? Is there a kind of model to be able to pre-screen it in a faster fashion, and how we can do that? And with the rise of AI, essentially there are new avenues in order to be able to predict the properties of molecules via fast surrogate models and machine learning. So it is not a new thing. Essentially, I mean, before the convolutional neural networks and AlexNet area and the era of deep learning, there were a lot of efforts in order to predict the properties of molecules with shallow machine learning. Essentially, a lot of ML methods like kernel-based, Bayesian, ensemble, and neural networks in a simple fashion of multi-layer perceptrons. And then most of efforts also were on the representation, how we can represent a molecule, what are the descriptors, how to get the labels and the training data. And essentially, these were the challenges even before the era of deep learning. And then there are a few challenges in the molecular machine learning world that I wanted to talk about. So one of the biggest challenges that we have is the enormous magnitude of chemical space. So essentially, the size of potential pharmacologically active molecules is around 10 to the power of 30 to 10 to the power of 60 molecules. And, you know, I mean, like finding a molecule that is active and works very well with the body. I mean, it's not toxic. It can penetrate the brain-blood barrier and all these ligand-based, you know, type of activity prediction is a very daunting task. If you look at, for example, GDP-17, it contains 166 billion molecules with only 17 atoms of C, N, O, S, and other halogens. And you can see the skeletons and hydrocarbons and the graphs and the total number of molecules here. And then you can see the GDP-17 here that is going there. So one of the challenges is that the space of even feature is super big. Like, I mean, the number of molecules that we can generate. The second big challenge is insufficient and noisy labeled molecular data due to very time-consuming experimental setups or wet lab or simulations. If you wanted to run DFT, it takes 48 hours, 96 hours, I mean, to run one DFT calculation for a molecule. In experiments, if you wanted to experiment the toxicity of a molecule, it takes a lot of time. So label is very expensive to acquire. So what we can do here to get the labels essentially is one of the challenges that we have. So two challenges: big feature space, like, I mean, big number of options or candidates to screen. The second is that as far as machine learning is concerned, which is about having a decent number of training data points, you need the labels, and getting the labels is very expensive. So what is the solution? I mean, like everyone in the community is thinking very deeply about these two problems. So the solution is that one of the ways that actually my lab and a lot of folks recently are looking at is about the number of compounds that are synthesizable is increasing dramatically. If you look at the PubChem, for example, on the number of compounds, you can see that they are increasing rapidly. For example, if you look at the ANI1 paper on the angular distribution, you can see that it's huge data set that is created on the molecules itself. And then if you look at the PDB for the protein data bank, you can see that a huge increase in the number of data that is deposited, or crystal structures that are deposited there. So the first challenge, which was like candidates, it seems that we have a decent amount of number of data points that we can play around with. So the question is that, can we make use of large unlabeled data for better ML molecular representation? Because if we solve the problem of representation and learning of the structure, then possibly it may reduce the barrier for the property prediction, as I'll explain. And the answer to this question is yes, by self-supervised learning. So essentially, a technique which is very, very hopeful in order to be able to predict the property of molecules by learning the representation without the labels. So what is self-supervised learning? I mean, many of you may know about this, but I just briefly explain how it is done. So in the supervised learning fashion, you know that you have an image, for example, image of a cat or a dog, and then you have the manual annotation that you put the label cat, dog, and cat, and then you have a XY pair. So X image, Y, the label. And then, as we mentioned, like in molecular molecular property prediction, this part is not as easy as images, right? I mean, so you can have anyone go and, label a cat or a dog, but I mean, you need to spend a lot of time and energy and money in order to predict, for example, the toxicity or get the label for the toxicity of a molecule. On the other hand, self-supervised learning is that you don't care about getting the label, essentially, at this stage. And what you say that I can write an automatic, kind of like a script, for example, and rotate, for example, this cat, right? I mean, 90 degree and 180 degree, and create the label. So the label can be prediction, or the label can be that how much actually this image is rotated. We don't care if it is a dog or a cat, we only care about the task, that how much it is rotated. So in this way, through this practice, what is happening is that essentially we are able to learn the representation of image. So we are able to learn the features that are associated with the images. And that is equivalent in chemistry and material science. Is equivalent that a person has spent a lot of time, on learning about the molecules, about how they are represented, and then they go and, for example, they wanted to do perovskite discovery, or they wanted to predict the toxicity. Their knowledge, their overall knowledge of molecule structures and organic molecule is super good, and then it takes a small amount of time, to learn to a specific domain, which is, for example, toxicity prediction. With a few experiments and with a few, the training, you can just make this person a kind of like expert in this one, compared to a person that doesn't have any knowledge of chemistry and you wanted to talk about the, toxicity. So inspired by this, idea of learning on top of the molecules themselves without their labels. So what we did is that we have created we have used unlabeled database, and in the first step we did the SSL pre-training with the SSL objective, which I'll talk about it. There are different ways to do the pre-training, and then in the second step, essentially you can copy the weight or pre-trained actually weight of the neural networks, and then predict the properties, which is what we call downstream fine-tuning. So inspired by that, I mean, last year, I mean, we worked on developing a body of work on contrastive learning via graphs, which we published in Nature Machine Intelligence and JCIM on the contrastive learning of molecules. And then today in my talk also, I'll talk about the multimodal learning, essentially how we can combine the language models with the graph-based models, transformers with the graph-based models. And the last part of my talk, the third part, will be completely departing from graph representation and going to the rich language features. And in all of them, SSL, self-supervised learning, is an evident part of the technology that we use in predictions, and also we played around with the feature representation, and as I mentioned before, feature representation or representation has always been one of the big challenges in molecular machine learning. So in the first part, I'll talk about the contrastive learning efforts and the graphs. Second part, I'll talk about multimodal, multi-view learning with the language models combined with the graph-based models. And the last part, I'll talk about completely rich language features and using the large language models. So we introduced MolCLR, in which actually you have, for example, SMILES of a molecule, two SMILES of the different molecules. You can build the graph, for example, molecule graph G1 and molecular graph GN, and you can do that for all these molecules. Then you can apply augmentation. Obviously, there are different modes of augmentation you can apply. You can do the masking of atoms. You can do the masking of bonds. You can remove the subgraphs. And then you can do it for all these molecules. And then you can pass it through a GNN encoder and have a readout on the latent space H1 up to Hn. And then what you can do here on the latent space, you can use the contrastive learning that was used in the MolCLR paper by Jeff Hinton in 2019, that you can say that, hey, I mean, these molecules that they are augmented, they are essentially the same. So I can make them attract each other, or they be similar on the latent space, and then I can say that, okay, these two molecules are different from each other inherently, so they should repel each other. So to explain it in a better way, first I should go over different kind of modalities of graph augmentation. So you can actually mask an atom, as I mentioned. You can delete a bond, or you can do the subgraph removal, and then you can use a graph neural networks backbone with the message passing. I'm not going to go through graph neural networks because all of you are super familiar with it almost. So you can essentially augment here and then use the graph neural networks in order to encode it and take it to the latent space. Two different molecules, each of them has been augmented, for example, via a different strategy. And then on the latent space, what is happening is that you can say that, okay, this is my original molecule. I'm going to do, for example, subgraph removal. Then I take it via graph neural networks to the latent space. I get this point. Then I do another one. I get another point. And these two things are similar to each other, so they should attract each other. So they should be closer to each other on the latent space, because inherently they are coming from the same source. On the other hand, if you have another molecule, you do augmentation. Essentially, these are completely different molecules from the first molecule. So on the latent space, you have a big distance, and then these two things should repel each other on the latent space. And what you can do is that you can define a score function between these two molecules. And then what we use here in this paper is the normalized temperature scale cross entropy loss, NTXNT, which you can calculate the cosine similarity between the two, between the latent space of the two similar molecules, and you have a temperature scaling here, which you can use, and then you can divide it by the sum of actually these cross entropy loss. And then what we did is actually we pre-trained on 10 million molecules from PubChem. So it was a huge pre-training that we did using these things, and then we augmented it, and we did the pre-training. And then for the fine-tuning stage, we applied it to molecular net benchmarks. I mean, at the time that I was at Stanford working with Vijay, Zheng Guen came up with this beautiful paper that we did the molecule net in that time with different kind of data sets, that it becomes somehow a standard benchmark right now in molecular AI drug discovery. So, so the first thing, Prudential, what's the question?
Oh, so, yeah, sorry. I have a question about the previous slide.
Sure.
The one before, sorry.
Okay, this one.
Yeah, so I was wondering if you took any particular measure to kind of make sure that the positive, what attract actually attract and what repel actually repel.
Yeah.
Because like in the time we can do an augmentation, assuming that those two things kind of attract each other, but in reality they might be closer or further than
Exactly. Yeah, that's an amazing question, and we answered it actually in a follow-up work called MolCLR. So we inform it via the distance. You're right. I mean, one of the difficulties in pre-training and SSL is that to what extent things are negative or positive with each other. For example, a dog and a leopard are not similar, but they are not completely negative compared to a dog and a sky image, right? I mean, so those are completely negative to each other, but a dog and a leopard, I mean, both of them are animals. I mean, they have a lot of similarities. So I'll talk about that in the improved actually MolCLR, which we did, and that's a paper also. So in molecular net classification, you can see that we did different kind of studies on the graph convolutional neural network backbones and GIN, and we did the pre-training. And as you can see that in most of them, I mean, MolCLR performance is doing very good. We did it on regression task, I mean, for the property prediction. As you can see, it is also doing the decent work in terms of both pre-training and, you know, I mean, applying the MolCLR GCN and GIN. We use two different kind of graph neural networks as the backbone, GIN and GCN. And as you can see here, especially GIN is performing very well here in many of the tasks that we have. We did also ablation study on the augmentation. So on the augmentation, essentially, you can do different, as I mentioned to you, there are two hyperparameters to look at. One of them is that, okay, which of these augmentation technique is much more effective? Essentially, is it atom masking or bond deletion, subgraph removal, and to what extent? So essentially, you can delete a lot of bonds, right? I mean, to kill the molecule completely, or you can, you know, for example, remove big subgraphs, 25%, 50%. So as you can see here, for the especially MolCLR with the GIN backbone, you can see that with no pre-training, the ROC AUC is very low, but with some effective pre-training, for example, on the clean talks, you can see that subgraph removal with a 25% is getting us a very high, you know, accuracy comparable to a lot of SOTAs in this one. So as Prudential asked, I mean, the question is that, okay, there is a problem here, and that is to what extent, I mean, things can be negative to each other or positive or attract or repel each other. So, and this is a problem that we call it faulty negative mitigation, essentially. And that is like, I mean, you need to have a baseline or a standard in order to say that to what extent a molecule or a fragment can be negative or positive. So we introduced a concept called fragment contrast. In the fragment contrast, I mean, we defined an anchor fragment, and then we essentially modulate or inform the latent space about how similar these are together. So essentially, we have an anchor molecule which you can use, I mean, bricks or other techniques in the RDKit library in order to break the molecules into multiple fragments. And then you can say that, for example, this molecule is negative this much to this fragment, and this one, I mean, the other one is quite negative. And then this is called faulty negative. This is called completely negative. And this is called what we call it faulty negative mitigation, in which we say that this molecule is closer to the anchor molecule, but this molecule is far away from the anchor. And the way to include that, I mean, the way we include it is like, I mean, we have this thing called physics-informed neural networks, but here is somehow similarity-informed latent space for the contrastive learning, in which you can create a weight I and with a subindex of I and K, and then you can actually calculate the similarity between the two molecules or two fragments. And you can use ECFP plus Tanimoto similarity and subtract it from 1 and embed that weight into the loss function, into the weighted cross entropy loss function here. And as you can see, the way that we applied it, it's actually chemistry informed or similarity informed weighted cross entropy, in which we tell the latent space, hey, this is your distance, or this is your negativity or positivity with respect to that. So we did the fragment contrast, as I mentioned, to also one of the big things here that enables us is also to work on much more larger data set, because you're working also with the fragments, and then you can create different kind of anchors at different locations and measure the negative. So your data set augmentation will also become much more higher. And then, as I mentioned too, you can use the bricks decomposition, which is a beautiful algorithm in order to do this fragmentation. So we compared the MolCLR versus MolCLR on classification, and you can see a significant jump also in the accuracy in most of the tasks on classification, and also on the regression we had great progress. So this was the first part of the talk that I wanted to talk about. Then the second part is multimodal learning, and I wanted to get into the business of transformers, which is pretty exciting things that is happened to AI by this amazing paper, Attention is All You Need. And as you know, I mean, the biggest problem that transformers solve is the sequential computing problem, in which, I mean, in LSTMs and most of these sequential problem solvers algorithms, we had a lot of dependencies on the back propagation, in which they killed either the gradient by vanishing gradients or exploding gradients. And then transformers, with a beautiful idea of attention, I mean, they were able to solve that problem. And since then, I mean, as you know, I mean, we had a lot of different renaissances in different kind of language models. For example, we have BERT, which is a masked language model, with its super interesting SSL modalities of using CLS for predicting a word and essentially predicting a sentence afterwards. I think, I mean, those are very exciting discoveries, or essentially technologies that happen to the large language models, that you can run an automatic scripts for the pre-training over a large corpus of language or text that is available over the internet or in different areas. And I think, I mean, BERT is one of these exciting things that has happened, coupled with the transformers. So we have seen, I mean, after renaissance of the transformers, there are a lot of architectures that have become popular beyond the natural language processing. So, for example, VIT, which is Vision Transformer in 2021, mask autoencoders. And then we saw a lot of actually efforts in the molecular machine learnings and about the SMILES. So we had the SMILES BERTs, we had ChemBERTa, and also ESM 1B transformer that has recently been published. So it's not only, I mean, the effect of transformer was not only on the language models, but also they diffused into vision and also molecular machine learning and protein modeling and prediction. So one of the questions that my lab also worked on is that how we can use transformers for chemical compounds. specifically polymers. So if you look at the polymers, so you see that there's a huge heterogeneity in the way that you can present a polymer. So polymers have random structures, they have alternating structures or block or graft, actually copolymers, and there might be experiments at different, temperatures. And also another branch that I will talk about today is metal organic frameworks. So these two type of materials, polymers, which is completely organic, soft, and then also metal organic frameworks, which are organic, inorganic structures. So let's see how we can use effectively the information like 3D geometric information with the language models. So the first part of the work that I'll talk about that is published in Nature Computational Materials Science is the transformer-based language model for polymers, which we call it transpolymer. So one of the interesting way that we did this is on the tokenization space that we represented, for example, a polymer with the smile of its monomer, and then also we were able to encode the ratio and the type of the polymer and for example, tagging parts, and then different components if it has a copolymer number to ratio, type, and also the temperature that it is a material descriptor. So one of the great things about the language models is that it is, because of its power in positional dependency, taking care of positional dependencies, you can put all these stuffs in a kind of like a structured way, but you can put them, at the beginning or at the end. So that's a great benefit. And then we tokenized it like this, and then first of all, we again used the pre-training power. So we created a lot of polymer sequences, and then we used the mask language model. We used the transformer, and we had the prediction head, and we get the token, and we pre-trained it on 1 million polymer data augmented to 5 million total pre-trained data. And then in the second stage, similar to the contrastive learning work, MolCLR, what we did is that we got the polymer sequence, we got the pre-trained, and we fine-tuned it to the property. So our experiment showed a significant improvement, specifically in the realm of polymers, that the data is very scarce. So the data availability is very low. For example, in one data set, PE2, we only have 271 data points. Or for example, for conductivity, we only have 9,000. Or electron affinity, we have only 300 essentially data points with the labels. So as you can see, I mean, like this is the baseline, and transpolymer, which is our work starting from scratch versus pre-training, you can see a significant enhancement in reduction of, RMSE or root mean square error. So, and then we did this ablation study on the number of pre-trained data. As you can see that there's a significant increase, for example, in the R squared value. For 5 million data points, we have a significant, enhancement in the R squared. And then for the other tasks also, you can see the same things. So speaking on the effect of pre-training, so you can see here the latent space of the pre-training for 5K pre-trained data. You can see there's a value, or there's a gap here between the data points that we have for pre-training. The ones that are in gray are the pre-trained values, and the ones that are in different colors are essentially the fine-tuning tasks or downstream tasks. And then with 50K, you can see we have a better coverage of the latent space, and with 1 million pre-trained data, you can see that the whole gap is filled, and now we have a better coverage, and then the prediction accuracy becomes more. So this was the first part of the second part of my talk, which was about how to represent a polymer. The second work that we did, and is published in Journal of American Chemical Society this January, is multimodal learning on MOF and using MOFs, so which we call it MOFormer. So essentially, if you think about a metal organic framework structure, you can present it both via a structure, and you can also use something called MOF ID, which, for example, each structure of MOF is presented with QMOF. For example, this structure is presented by QMOF 252.1623, and then you can essentially tokenize this with the topology and smalls of SPUs into a language feature, and then use a transformer in order to pre-train and then attach a regressor head and do prediction. So the way that we did it is that we use the MOF ID. As you know, I mean, metal organic frameworks have the inorganic building block, organic building block, and then you can put this all together, in order to build a language descriptive of the structure in a kind of automated fashion. So by doing that, you can view it as this interesting viewpoint that, okay, so you can have the structure, you can use, for example, CGCNN, which is a convolutional graph, crystal graph convolutional neural networks. You can use that as an encoder to encode the structure, 3D structure of MOF. You take it to the latent space, right? And then on the other branch or on the other mode, you have this text description of the same structure. And you can use the text description of the same structure, pass it through a transformer, and with a head, you can make an embedding. Then essentially these two are different views, right? I mean, so in the multi-view or multimodal machine learning, essentially, if you wanted to classify a cat from dog, you can use both the images of a cat and dog or the voices of cat and dog, right? So, but what will happen if you use both modes? So, is the learning synergistic? So, or can we do it better via using both modes if we have the data availability? So the question is that, okay, so how do you train this, network that has two branches? You have an encoder and projector for the CGCNN, and you have an transformer encoder similar to BERT that you can train and get the latent space. Then essentially these two things, since they are equal on the latent space, they should be equal. So if you multiply the embedding ZA and to the embedding ZB, then you have a cross correlation matrix that is here, and you can back prop, or you can actually automatically differentiate this and back prop this to make it an identity matrix. Why identity matrix? Because these two are coming from the same source. So they, on the latent space, we assume that they are the same identity. So you can calculate their cross correlation matrix, and using a loss which was in this interesting paper in ICML 2021, you can use Barlow twins in order to make it an identity matrix, essentially shutting down the off-diagonal values. And then there are a lot of benefits to the multi-view, multimodal pre-training. One of the big benefits is that, first of all, each branches can be used separately from the other branches. So you can either use if you have the structure, you can use the branch of a structure, or if you only have access to the MOF ID, you don't need a structure. Actually, this is after pre-training, you can fine-tune it for any kind of downstream tasks. And so what we did is that we pre-trained it for 410K metal organic frameworks, actually structures, and we showed a significant actually enhancement in the prediction of band gap and gas absorption predictions here. And you can see that it was able to predict better than SOAP and CGCNN from scratch and pre-training. Also, we did this ablation study that what will happen if you don't pre-train and start just from scratch, or with the pre-training, so that to show the effect of the pre-training on this. Okay, that essentially wraps up the second part of my talk, and the last part is completely migrating from the graph neural networks and seeing how we can describe molecule or crystal structures or using the text language, if you want to think about it. And that is inspired by the fact that in some days I was thinking about the water molecule, that if you wanted to show the water molecule and, for example, predict its freezing point, right? The way that we can represent the graph molecule to predict its freezing point is that you only have two bonds that you can define via graph, and then you can load a lot of features like the partial charges and elements of like what is oxygen, what is hydrogen, and then predict the property. And but if you wanted to use text to describe water molecule, you can write a book, right? I mean, there are hundreds of books about water. Water is the molecule of Earth. It covers 71% of the Earth's surface. I mean, like water. I mean, is a compound that has two hydrogens and one oxygen, and then its angle is 105. I mean, like its partial charge. So you can really qualitatively describe a molecule or a crystal in a much richer format. And inspired by that, and then first of all, that was not possible before the renaissance that we have in the large language models and the natural language processing, because one of the biggest challenges was this dependency of these sentences to each other. So, for example, before it was not that much practical to for example, shuffle all these sentences, or there was a position there was this positional importance and sequential dependencies that, for example, LSTMs needed to back propagate through, and their exact position was important. But now, actually, with BERT and a lot of these possibilities that has happened, you can describe, for example, a system like a catalysis system here. So, for example, if you look at this catalysis system, you can see that you have a surface here, you have a primary interacting atom, and you have an adsorbate, and then you have secondary interacting atoms. And then you can, with the help of a lot of text description generators, for example, ChatGPT is one of them, or RoboCrystallographer is another one, you can write a script, or you can write an automatic script to inquire or do an inquiry about different components of a molecular system. So we can, for example, you can find the adsorbate is NO. So can you tell me, hey, ChatGPT, can you tell me what are the molecular characteristics of NO? The molecule has a linear geometry with a bond angle of 180 degrees. The bonding type is is covalent. So then you can go to the surface, right? I mean, you can say surface type of Ti6 PD2, once there is valence electron number and electronegativity, then the ChatGPT will tell you the type of surface is BCC, the coordination number is 8, surface. So it gives you a lot of description of this system that not necessarily you can use or apply them to the graph. So that's a big advantage. And how to harness that advantage compared to the graph representation is a question that we are thinking about it now. And as you can see, I mean, like in this work that is right now under review in ACS Catalysis, and then it is on archive, and I posted it on Twitter. You can see that, I mean, you can essentially inquire from different sources and then assemble a rich representation of the text, So the framework is that, for example, you can take a structure from OC20 dataset, which is a catalysis dataset. You can go ahead and, break it into multiple parts and do the textual data. Then, I mean, there's a wide array of different kind of pre-trained, large language models like Alberta, RoBERTa, BERT, and usually, I mean, our experiences, best practices is that RoBERTa is doing really well in many of these cases based on the ablation studies that we did. And then you can go to the energy prediction. So it's very exciting that you can go from a huge text description to the, for example, prediction of the energy of the task. And that is actually a kudos to the neural networks. When I'm teaching it in my class, the first thing we say is the universal function approximators. And you can see it obviously here that you can go from a rich text of description to an energy property, which is super amazing. So, excuse me. So you can have the string, the description, you can tokenize it, you can use the pre-training using RoBERTa, and then you can have the regressor head and predict the energy. Our initial work, which we call it cat-PERTA catalysis with the RoBERTa, and comparing to the GNN was very interesting. I mean, for lower amount of data, we got somehow comparable results with the cat-PERTA compared to the, for example, CGCNN and some benchmarks like SCHNET and DIMENET. And as you can see, I mean, this is some of the benchmarks that we did. There were a lot of exploration featured through textual format. For example, should we put the string number 1 adsorbed smiles and then the bulk composition Miller index, or should we do, for example, primary interacting atom site type? How about, I mean, adding, for example, secondary interacting atoms into the values that we are calculating, and then so on. So we did this ablation study that you can find it in the paper. Between the two descriptions, for example, description 1 contains general information and does not derive from adsorption modeling studies, and then there is a description 2 which includes properties utilized in adsorption modeling. Then the description 2 was better than description 1. Based on what? Based on the MAE, or absolute value of the two subsets that we have on the description 1 and description 2. So we did the comparison with GNN. So the error is still higher than some of the GNNs, but we hope that there are a lot of other follow-up works and the community can do this, essentially by pre-training more, by augmenting the data. So we haven't yet augmented the data sets in the language models. I mean, you can do a lot of different kind of modalities of augmentation. And this is still a very, very start work or initiative that we have here in order to completely go away or depart from graph and to see that if it does well or not. And it's at earlier stages to say that, okay, this is going to perform better than graphs or vice versa. So still a lot of things needed to be done here. One of the big benefits also to use the transformers and language model is the interpretability compared to the graph. So essentially you can go ahead and look at the attention scores, and find out, I mean, like what are the words that it is attending to. And actually, for example, hydrogen, surface, nitrogen, you can see that they are popping out. Bismuth, for example, is important. Also, the effect of, again, fine-tuning versus pre-training is here very obvious. So this is the latent space colored by, for different categories, for the catalyst type, for the split, for adsorbed sites, and adsorbed type. And you can see that separation that is after fine-tuning happening is pretty enormous. For example, for the adsorption type, you can see this is before fine-tuning, essentially learning using MLM, which is mass language model. And then after you fine-tune, you can see that they are completely getting separated. Another effort that we recently, 2 weeks ago, we put it on archive, is that we use almost the same strategy for the molecule nets. Essentially, we spend a lot of time, 3 to 4 months, finding the description by using the GPT, chat GPT, essentially API, and we paid actually for the paid version of it, and we parsed 320,000 molecules from MoleculeNet on different tasks, as you can see here, for the regression task, ESOL, FreeSolve, and lipophilicity. And the for classification, we did HIV, base, triple BP, tox21, cider, and clean tox. And then the way that we did it was that we essentially asked the chat GPT. Also, we did a lot of prompt engineering. I'll show it in the next slides. For example, we said you are able to generate important and verifiable features about molecular smiles. that made a significant difference if you don't tell that, or if you don't prime the chat GPT with that. So, I mean, you can see that it says, certainly I can provide important and verifiable features about molecular small notation. If you have a specific small notation in mind, need information about a particular molecule, please provide a smalls. Then you can say, generate a description about the following smalls molecule. So if you don't do this prompt, I mean, you can go and test it yourself. So you'll see that there's a big difference. So there's a prompt engineering that you need to do in order to get that. And the paper is on arXiv. It's called GPT MolBERTa. And also the data set, we released the data set. So it's 320,000 molecules. We recorded all its chat GPT description, and it is available. So I asked the community here to go, I mean, like, do a lot of different ideas, augmentation, contrastive learning, multimodal. There are a lot of things to do, and it's a very exciting time. So, so something to note is the prompt engineering, as I mentioned. So, for example, you can do in the iteration 1, we did the role system content, and then give a description of the following molecule value. And then we saw that, okay, the performance of ChatGPT is not that great. Then we changed it like this to iteration number 2. The second iteration is we said, okay, role system content, you are an expert in everything about molecules. So we primed it like that. And then we said, generate verifiable information. So these words that we put, I mean, has been a lot of iterations of talking to the ChatGPT to see which actually prompt is giving us the best actual response. And then, for example, here, the third iteration was you are able to generate important and verifiable features about molecular SMILE. So this gave us actually holistically a better response. So, and then generate a description about the following small molecules, but the second, thing. And then you can see example of molecular description that it gives us. And, I mean, because it's a lot of molecules, it's 320,000 molecules. I mean, so you need to make a single type of, prompt that works for all these molecules. And that's a daunting task. So our benchmark, I mean, against like our own MolCLR and a lot of SOTAs in the graph world and also in the language models, which you can see, I mean, there are a lot of language models also right now. I mean, there is MolBERT, BERTa, CLM, self-former, and our model, which is GPT MolBERTa. So we didn't see a language, I mean, like on ClinTalks, it's not doing very good effectively. CLM is doing very good, I mean, like on BBP. But if you look at the GPT MolBERTa, it's comparable to our own MolCLR, actually. It's 74% actually accuracy. So it's very promising, compared to that. And then on the other task also, we are not that much bad currently. I mean, this was the first iteration that we wanted to put the paper out, but obviously there are a lot of different ways to augment and make it better. But on the regression, actually, we got really, really good results. So compared to for the freesolve, eSol, and lipophilicity, these are actually the value of the RMSE we got. I mean, as you can see, I mean, they're lower than all of the existing models. I mean, it's 0.896 and it's 0.477. Yes, Prudential.
How do you explain the fact that the model is so better in regression setting compared to classification?
Currently, I mean, so this is very fresh out of the oven, Prudential. I don't have a good explanation, but we did a lot of tests, here, and I think, I mean, on the feature space, it makes so much, because it is a very rich text, it is making so much differences that is correlating with the regression values. But for classification, I mean, compared to all the graph models and, for example, a SNET in the BBP or CLM, it doesn't make that such kind of difference. It is something that we are still working on, but it's very promising that, especially for the regressions, we are getting such kind of good results now. But I mean, I think, I mean, we need to investigate that more. we are doing some investigation like on the interpretability to see, for example, this is the attention scores for one of the heads. You can see that, for example, it is attending to the smiles, to that its molecules, to these numbers, nitrogen, solely, for example, here you can see that these are some of them, and then most of the like propositions and like, you know, I mean, non-important stuffs are not attended to. So in conclusion, I showed that SSL for different molecular representation, for mass language modeling, for contrastive learning, for multimodal 1D plus 3D. So what I call 1D is the text of, for example, MOFs versus 3D structure of MOF, and we can use Barlow twins. Then I showed SSL on large unlabeled data benefits molecular property prediction in various applications, for molecule net, for polymer property prediction, and for MOFs. That's what I showed. And the third, which is a recent effort, it's been a few months that we have started, is that completely departing from graph neural networks and talking, describing a molecule using a text-based features versus graph. And we have two works, one of them BERT, which is on the catalysis systems, which has an adsorbed structure, surface, and also the interaction in between, and GPT-MolBERTa, which is the molecular features are generated using AI, which is ChatGPT. The training also used RoBERTa, which is a large language model. So it's kind of completely end-to-end AI. So the features are generated by the AI text, and also the learning downstream task is also there. So for the acknowledgement, my lab essentially, you know, I mean, 3 PhD students who graduated, they did a tremendously large number of body of works, especially Yu Young on the MolCLR, Rishi and Johnny on MOFormer, and recently Hoon, my PhD student from chemical engineering, and Soraya, my master student who work on the GPT-MolBERTa. Thank you so much for your attention. I'll be happy to take questions here.
Perfect. Thank you so much, Amir, for the group presentation. I see a hand raised. Do you want to go first?
Hello. Hi, Dr.
Hello.
Farimani. So I had a question about GPT-MolBERTa. We are doing the same thing in our lab. Like not the same thing, very similar to what you've done. And I was looking at your results for the classification task. If you please bring it again, the page on classification.
Yeah,
yes,
here.
One of the things that I noticed, you didn't, for example, compared yourself with a more recent works on BERT models, for example, MolRoBERT. Give me a second, I will. Right. Okay. So, for example, MolRoBERT that weirdly has a lot a better performance in ROC on BBP or base. And then another thing that I noticed was that why GCN models, I'm also working on it, why GCN models are working not as good as, for example, BERT models, because I'm doing the same. Usually I noticed that the language models perform much better, which for me doesn't make sense, because in language, a text and a graph are transferable, right? You can change a text to a graph and a graph to a text. It is based on what I know. So can you?
Thank you so much. So I mean, like, these are the models that, I mean, like, so the model that you are mentioning is better than CLM, for example, for 3VP, is like more than 91%.
I think you are on mute. I think you are unmuted.
Sorry, yeah, sorry. So for example, this model that I'm saying is for 2023, and for the ROC for BBBP is 93
Oh, okay.
3.3. So it's
Yes,
a lot higher.
a lot higher than even
One of
CLM. Yeah, okay. Interesting.
yes,
I'll tell my students, thank you very much for noting that. I'll tell my students to do a, I mean, the field is moving so fast, you know, you cannot catch
yes, yes,
with all of them. So as I
yes.
mentioned to you, I mean, like we started the data collection, like I think somewhere in, it was beginning of April, you know, and so maybe these papers, I mean, that we were working on, I mean, we didn't see some of them coming. But most of them are working with the smiles. So the merit that we are
Yeah.
trying to show is that, okay, can you have a rich textual description, even like much richer than the smiles? And does that play as a kind of noise to the smiles, or this is actually a better description that we can take advantage of? So that was our goal, and you can see we already defeated in all of this almost. Like, I mean, we are not as good as other
Yeah,
ones.
GPT is not. Another thing that I can suggest, that's what we are doing, is adding llama maybe. They are also can like generate text like GPT, and at least I think it will be a good comparison with your model
Yeah,
to see if llama is doing better, and it's free. You don't need to pay like
sure,
ChatGPT.
absolutely. We will do,
Yeah.
we'll use definitely that one. Another idea is that we are working is multimodal, like combining, as I showed you on MOFormer, you know, we combine the structure and the text representation, and we synergistically learn it using Barlow twins. These days, clip loss is much more better in terms of, like, I mean, doing the multimodal learning. So we are using clip with the GPT MolBERTa and MolCLR in conjunction. We would see the results, what's going on. But I hope that it becomes
Yeah.
synergistic, doing better than both graph and the textual representation.
Yeah. Thank you. It was very
Sure.
informative, your presentation. Thank you
Thank you.
again.
Razvan, we take that your question as the last one.
Hi, Amir. A really nice presentation. It was a pleasure watching it.
Thank
I
you.
was kind of wondering how do you see the future of the molecular ML field playing out? Like, do you feel like these like large language models are kind of like the future, or are we missing some key ingredients? You know, and and this whole thing.
That's a great question. I think, I mean, it's very for the I'm very hopeful about the language description versus, I mean, you can see, for example, CLM here. I mean, look at the triple BP results, or talks to anyone. I mean, like it's still, like, I mean, some of the methods like SVM are doing a lot of higher than even deep learning or graph. But language showed a lot of promise, and since it's early stage of the language models for the molecular drug discovery, I said that it's not maybe it's very soon to make a call that they are better than graph. So there are two avenues that I'm very hopeful. So the SSL should be there definitely, you know, pre-training. There is no doubt about it. That should be there in any way, either language or graph. We did it both, right? I mean, we pre-trained for the text, and we pre-trained also on the graph, and we got really better results in both cases. I think the future might be multi-view as well. Like, I think, I mean, the realm of multi-view, we shouldn't forget that it could be the synergistic learning between the graph with the pre-trained mode, and also with the text with the pre-trained. You can get the best word of graph and the best word of text, and then, you know, synergistically couple them, learn on the latent space representation of them by very interesting losses these days, like, I mean, clip loss. I mean, we saw a lot of promising results compared to the Barlow twin. So I think, I mean, that direction that we should definitely have pre-training. We might not go away from the graph, because graphs were really beautiful way of representing, and, you know, they are differentiable and everything. I really like them. Text showed a lot of promise now. I mean, I think, I mean, but maybe, I mean, a kind of like joint learning between these two things, that we take advantages of the greatness of the both worlds, might be the correct response. But I mean, I should tell you that I mean, these data sets that everyone on MolCLR is trying on is pretty saturated. It became really difficult to beat the SOTA. Sometimes, I mean, students become really demotivated. I see them. So we should, I think community should look at new data sets as well that are much more challenging. There are spaces to improve the model. I think, I mean, that's another challenge we have here. Yeah.
Are there any interesting benchmarks that are coming up now recently, like after MolCLR?
I don't know why. I mean, the community doesn't work, I mean, to do that. So I mean, at the time I was at Stanford, VJ, BERT, and I, and also Vengeance, we talked about this, and I mean, like, everyone is using MolCLR, including me myself. But I mean, like, I think our community is so much obsessed with, I mean, like, beating the SOTA, that they don't think about the new data sets. I mean, so there should be a new data sets. Like, I mean, and that is, I mean, like, in the world of machine learning and AI, it was the case, right? I mean, everyone on the vision wants to do the ImageNet, right? I mean, and they compare themselves with AlexNet. So that's because of being a pioneer in the data set creation. But I think, I mean, this is the right time to stop here and create much more challenging data sets. I think, I mean, the pharma industry, and then I think, I mean, industry can play a big role in creating those challenging data sets. But as far as I know, Razwan, no other data sets that everybody agrees on, you know, benchmarking.
Yeah. Thank you, Amir. Yeah.